Okay, today we're going to start talking about the solar system and the different thoughts of how the solar system is put together, and then we're going to move into the moon. So we're going to start by looking at a geocentric view. Geocentric view means that the Earth is in the center of the solar system, and the other planets and other objects orbit around the Earth, and the Sun and everything else in the universe does orbit. And a lot of that belief came from we don't feel like we're moving on Earth, and we see the Sun and the Moon and the stars in the night sky seem to turn or move through the night sky, so Earth must be in the center, and those other objects must then move around the Earth. They base their calendars off the constellations. Some constellations come out at different times of the year, so when those constellations would come out, then they would know that the change in the seasons is taking place. They thought that stars were holes in celestial spheres that surrounded the Earth, and that some of the planets were thought to have stopped moving for a period of time, a week perhaps or more, and then start to move again, or what we call now retrograde motion, where the planets appear to almost move backwards as observed from Earth, and then they would begin to start moving again. So that's what we called retrograde motion. As we continued looking at this, then we started to get into Ptolemy. Okay, first to predict the locations of the planets, but it wasn't a very, very good prediction. He imagined the planets on small circular orbits called epicycles. Copernicus's heliocentric model, okay, where he is going to, with the heliocentric model, put the sun in the center of the solar system, and then have the planets revolve around the sun. Okay, and this was the model that we use today, and it is much better for predicting where the planets are, or where the planets are going to be. So that's why it was more accepted then, because it was better at predicting where the planets were going to be. Okay, we're going to start to look at the way the planets move, and we look at Tycho, Kepler, and planetary motion. Now, with this, okay, they were going to Kepler is going to come up with this theory where the planets are going to move in elliptical patterns rather than circular patterns. Okay, and he's going to come up with his 3 laws of planetary motion. Those 3 laws of planetary motion: the first one, that the planets are going to move in elliptical orbits with the sun at the focus. The second law of planetary motion is going to be the equal area law. Each planet moves around in such a way that the imaginary line joining the planet to the sun sweeps over equal areas of space in equal periods of time. So even though their orbits aren't perfectly circular, they're going to, if you kind of look at it as like a pie, the little slices that they would cut out in the different time periods, the area inside their elliptical orbits is going to be essentially the same amount of area. And the third one is the harmonic law. This is just saying that for a planet to travel around the sun, we're going to look at the diameter that planet is away from the sun, and we're going to look at the period, or how long it takes. And if we take the period and in terms of years, and its distance from the sun in terms of astronomical units, then we can kind of see that they are going to be this relationship of a 2 to 3 relationship between them, where if we square the period or look at the diameter of their orbits, they're going to work out essentially the same. And that would be the harmonic law. Now we're going to get a look at gravity. Okay. Newton's first laws of motion and gravity. Okay, objects will move forever in a straight line at the same speed unless some external force changes it or direction or speed, so that things are basically going to move forever in a straight line. Now, we also talked about in class how that would really happen if we only had two objects and they were moving parallel to each other, especially if they were, assuming they're somewhat close to each other. The gravity of those objects will eventually cause them to change a little bit, and they wouldn't continue on forever in a straight line without ever meeting. That gravity, being an external force, would cause them to change. Okay, and then we talk about what gravity is here as a force of attraction between two objects with mass, and the strength of the attraction is proportionate to their mass and inversely proportional to the distance between them. So the big thing to remember there is that the two main factors that are associated with gravity is the mass of the two objects and the distance between the objects. So when we're talking about gravity, those are the main things we're going to be looking at, is the mass between the objects and the distance between the objects. Then we start to look at gravity a little bit more, okay, and we start talking about Einstein. While we talked about what gravity was with Newton, Newton never was really able to explain exactly how gravity worked, and that's where Einstein came along with his general theory of relativity. When he has here, he proved that gravity is just not this imaginary force that pulls objects together, but that it is actually going to cause the space and time around objects to bend so that they are essentially pushed together or fall towards each other. So that gravity is not an artificial stretching, or gravity is an artificial stretching of fabric and space-time by massive objects, which causes them to fall towards each other. We watched a little video on this, and just as a reminder, the video that we did watch, where they kind of stretched out some spandex and had the planets orbit around. So with that, you can kind of see here they're kind of showing how objects with mass would kind of bend that, and then you'd get other objects that would be able to orbit around. And that was one of the things as we're trying to show examples of how that would work. Okay, from there then we start to move into the moon. Okay, we had some different parts of the moon: meteoroids, craters, micrometeoroids, Marias, some of the physical features of the moon. Okay, mascons, Riles, rays, shattered areas that extend out. Regolith is kind of the sandy surface of the moon here, and I have some examples of that. And we talked about how the moon doesn't have an atmosphere, so objects like the footprints from the astronauts will always stay there unless something else acts upon those or changes them, such as like a meteoroid coming down on the surface, or someone else goes up there, another astronaut, and then changes those footprints. Because there is no atmosphere, there's not going to be wind, there's not going to be any kind of weathering and erosion, there's no air. The moon doesn't have a strong enough gravity to hold on to an atmosphere. Then we looked at the theories for the origin of the moon, and our best guess for the formation of the moon is that it was created when a smaller planet collided with Earth. The impact of the planet-like object broke a portion off of the Earth's crust, and we feel that that planet-like object that collided with the Earth was probably close to the size of Mars, and the Earth wasn't fully formed yet. Both planetary bodies were greatly deformed due to the impact and the great amount of heat during the impact. The Earth was able to reform, and it reformed very, very quickly. Probably took the Earth somewhere around 24 hours, or about 1 day, for it to reform. And this created a ring of broken rocks and upper layers of the Earth's mantle. Some pieces are still orbiting around the Earth today. The other thing that happened to the core of that other planetary object was absorbed by the Earth and actually added to Earth's core, giving Earth a larger than average core and a stronger magnetic field, which helps protect us again from solar winds. So this was actually a very, very beneficial thing that we had this collision with this planet-like object. that debris ring was made up of mostly lightweight materials, the upper layers of both the planetary object and the Earth, and it started to condense to form the moon. And this is why the moon is made up of a lot of lightweight rocks and doesn't have the gravity that close to Earth's. I mean, obviously being smaller, it's not going to have the same gravity, but its gravity is quite a bit less than what it should be, even based off of its size, and a lot of that has to do with it's made up of mostly this lighter weight rock. So that also goes back to this theory of what we call the giant impact theory. So the moon begins to collect this different rock, its gravity increases, and it cleans up almost all of that debris ring around the Earth, making the moon the current size that it is today. And we think that it took the moon about 1 year, give or take a little bit, to form, and that's kind of our best guess. And we watched a little video that talked about that, and they showed computer simulations and models explaining this idea for the giant impact and the origins of the moon. Then we start to look at section 2, and we're looking more at the phases of the moon. Okay, the waxing phases, the waning phases. Waxing as the moon gets larger. And we use the example in class of the Karate Kid with waxing on. If you're applying wax onto something, it's going to grow or be more visible, or the wax will be easier to see. And then when things start to wane, they get harder to see or appear to get smaller. They wane in sight, so the moon gets harder to see, or the visible side of the moon gets less and less. So we looked at our 2 phases of the moon. And then we have some of the other parts of the phases where we talk about the gibbous moon, where the moon is essentially swollen. We're in between the quarter moon and the full moon. So we also have the gibbous on the waxing side as we get closer to the full moon, and then we have the gibbous on the waning side right after the full moon. And like I have there, almost full. Then we looked at our eclipses. We looked at our solar eclipses and our lunar eclipses and the different parts of the eclipse. The umbra is the area where there's going to be a total shadow, and with a lunar eclipse, if the moon falls into the total shadow of the Earth, it often will get a blood red color because of the way the sun's light is refracted as it goes through the Earth's atmosphere. So it kind of will tint some of the red wavelengths of light and cast them onto the moon. And then there's the penumbra, which is the partial shadow, where not all of the sun's light is entirely blocked out from reaching the moon. And then we have a solar eclipse. That's when the moon moves between the Earth and the sun, and it casts a shadow onto the Earth. And again, with the umbra, that's the area where there's a total eclipse or a total shadow, and then the penumbra would be a partial eclipse or a partial shadow, where you would see the moon move in front of the sun, but it wouldn't completely move 100% over the circle of the sun. And here I have some examples of the lunar eclipse, where we can see the light from the sun coming down and casting that penumbra total shadow area, the umbra and the total shadow, and the penumbra around that, which would be the partial shadow, and I have it shaded in there in red, because as that light from the sun passes through the Earth's atmosphere, some of those red wavelengths of light will be bent in, filling in that shadowed area behind the Earth. And here we have our image of the solar eclipse, where we have the shadow from the moon cast on the surface of the Earth. And we could see that we have the penumbra, and then the umbra would be the total shadow, and that's where the moon would completely cover the entire disk of the sun. And the reason that the moon would be able to cover that disk of the sun, even though it is very, very small in comparison to the sun, it is much, much closer to the Earth. So while the sun is 400 times larger than the moon happens to be 400 times closer to the Earth. So that apparent, because the moon being closer, gives it that apparent same size as the sun, so it is able to eclipse the sun. Then we looked at the moon's orbit. Okay, and we said that the moon takes about 27 1/3 days to go around the Earth, but it takes it 27 or 29.5 days for it to make a complete lunar cycle, because while the moon is orbiting around the Earth is moving around the sun, so that causes that change in how long it takes the moon to go around the Earth. And the moon's orbit is slightly different than that of Earth's. It's about 5 degrees different, and that's why we don't have an eclipse all the time. So if you have any questions, please let me know. Have a good